Hello, thank you so much for tuning into my YouTube channel. In today's video, we're going to have a deep dive into hyperspectral image processing techniques in Python. And we're going to talk about what hyperspectral imaging is, how we could handle them and visualize them and normalize them, and also how we could apply PCA to them. Let's get started. As I said, in this video, we're going to have a deep dive into hyperspectral image processing techniques. In this video, we're going to explore hyperspectral images in ENVI-format, analyze data, normalize it, and perform dimensionality reduction using PCA, and also provide hands-on coding demonstrations for all these steps. Hyperspectral imaging captures data in hundreds of narrow spectral bands across the electromagnetic spectrum, unlike traditional RGB imaging, which uses only 3 bands. This technique enables detailed analysis of material properties, spectral signatures, and much more. For this tutorial, we'll use a hyperspectral image in ENVI format. It includes an image file and a header file in HDR format that stores metadata like the number of bands, wavelengths, and spatial dimensions. Okay, here is the dataset and environment setup in Python. We first import the libraries we need. Spectral library is the one that's used to read the data. And this is how we load the ENVI image. As you can see here, we use the header file to load the image. And then we convert it to the NumPy array and delete the last band. I'm deleting the last band because mine has a nan in the last band, but you might not have to do that. Let's run this section and see what happens. As you can see, it's warning me about the nan values in my data, and I already removed them. So as you can see, this is the shape of our data, and then the modified shape. I removed the last band, as I said. Now, visualizing. Hyperspectral images often contain hundreds of bands. Visualizing individual bands helps identify key spectral features or check data quality. Here is an example of visualizing a band. And as you can see, again, I excluded the last band. So I'm visualizing the 50th band. Let's run it. As you can see, this is band 50. So each band corresponds to a specific wavelength in the spectrum. Here we use band 50 as an example. But you can loop through all bands and focus on bands relevant to your analysis. Visualizing bands helps us see spot noise or artifacts in specific bands, or verify the spatial structure of the data, and also understand the reflectance distribution at a specific wavelength. Now let's also touch on extracting spectral signatures, which is another way of visualization. Each pixel in a hyperspectral image represents a spectral signature, a unique pattern of reflectance across bands. Let's extract and plot the spectral signature for a specific pixel, as you can see here. So I'm going to extract the pixel located at 100 and 100 spatial location. Let me run this part. As you can see, this is a spectral signature at the point 100, 100. So it would be almost here, 100, 100, somewhere around here. And this is the spectral signature. So in hyperspectral imaging, a pixel contains reflectance values across all the spectral bands. These values create a curve known as the spectral signature. It's crucial for identifying materials or detecting anomalies. It is important because different materials have distinct spectral signatures, allowing for material classification, vegetation analysis, or mineral identification. Visualizing these signatures helps verify data integrity and interpret results. Another topic that we're going to touch on is normalizing hyperspectral data. To ensure consistency and compatibility with machine learning models, hyperspectral data must often be normalized. Normalization scales reflectance values between 0 and 1. So that's how the data is going to be normalized. As you can see here, they're going to be normalized between 0 and 1. So for that, I'm going to be using the library scalearn. So we first reshape the data, and then we scale it using the mean and max values, and then we normalize it here. Let's run this section. So the data is normalized now. Now the last topic that I want to touch on is dimensionality reduction with PCA. Hyperspectral data often contains hundreds of spectral bands, which makes processing computationally expensive and prone to redundancy. Principal component analysis, or PCA, is a statistical technique that reduces this high-dimensional data into a lower-dimensional representation while preserving most of the original variance. PCA achieves dimensionality reduction by finding a set of orthogonal axes called principal components that maximize the variance in the data. These principal components are linear combinations of the original bands. Suppose your hyperspectral data is organized into a matrix X of size n by b, where n is the number of pixels spatial locations and b is the number of spectral bands. PCA transforms the data into a new set of variables z, where z is this one. Z is equal to x multiplied by w. Z is the transformed data principal components, and w is the matrix of eigenvectors corresponding to the covariance matrix of x. So to do the computation, we first compute the mean standard data, as you can see here, where mu is the mean of each band. And then we calculate the covariance matrix, as you can see here. And then we compute eigenvalues and eigenvectors of matrix sigma, as you can see here, where this matrix is the diagonal matrix of eigenvalues. And then we sort the eigenvalues in descending order and select the top k eigenvectors to form the matrix W. For dimensionality reduction, we project the original data onto the top k eigenvectors, as you can see here. We use PCA to reduce the redundancy and for efficient visualization and also for noise reduction. What do I mean by reducing redundancy? What I mean is many hyperspectral bands are highly correlated and PCA captures the essential information. What I mean by efficient visualization is that the first three principal components can often approximate the data well enough to visualize in an RGB-like format. And then lastly, what I mean by noise reduction is that PCA inherently reduces noise by discarding components with low variance. Okay, let's implement PCA on the hyperspectral data. So to implement PCA, we again use a sklearn library, and then this is how we perform the PCA. And then I'm going to show the first three principal components as an RGB image. Let's run it and see what happens. This resulting image visualizes the first three principal components as RGB channels. These components capture the majority of the variance in the original hyperspectral data, providing a compact representation for further analysis. By reducing hundreds of bands to just a few components, we save computational resources while maintaining the key features. PCA transforms high-dimensional hyperspectral data into fewer components while retaining most of the spectral information, as you can see here. And it's also worth noting that the first principal component typically captures the largest amount of variance, while subsequent components capture finer details. And that's about it. Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.